Morning.
Drin.
So time is now 3 minutes past the 10 hour, 10 o'clock, and I'll think we start. The whole session will be recorded and will also be put on our repository, and if things looks pretty okay, we might put it on YouTube as well. The question here is the slide that I showed here. Is this on a reasonable size on your screens, or do I need to make a full screen?
Small for me.
I don't get any feedback on it. The size is pretty okay. Then I would suggest that you all mute your microphones.
It's too small.
It's too small? Or you want to run it this way?
This is fine.
Yeah, much better.
Okay, then we do it this way.
Can you hear us?
I will just try to remember what slide then, so I can make the presentation noisy. I would ask you to mute your microphones, so we don't have a lot of noise. If anyone has a question, whenever, please open your mouth and unmute your microphone and interrupt me. Another way is to write something in the chat. So what I would like to provide this roughly 2 hours is an introduction to the Arrowhead Framework. It's kind of a crash course, so it will at a number of places be pretty fast. And it will not be complete, but it's a way of hopefully getting more people a brief understanding of the Arrowhead Framework and what's the things behind, why was this done, and which are the kind of key important architectural definitions and approaches that is used. And then we'll look into some of the details, and at the end we will look into where do we find documentation, code, resources, how to use these things, and we will also announce a follow-up situation of this crash course. Anyone having a question so far? No? Let me run then. So first of all, it's pretty clear that there is a need for new technology with all this digitization, Industry 4.0 and so on. And this is very much connected to these enterprise situations, which will tend to be multi-stakeholder operations, and a company is not doing everything on their own, and there is a need to integrate different companies, different players along the supply chains, the product cycle, and from the shop floor to the business. So this is where we are starting from. And it's also pretty clear that we do need information feedback to support this. So there's basically the three axes on the previous slide, and that there's a need to integrate all those in various level ways, and that the flow of information here will never be static. We may define a number of paths at the same time, but those will be for some time, and then we need to change. And this is there is a number of people who are still. I will try to mute audio for those who still haven't done that. Yeah, good. Another way of viewing this is that operational technology in our production environments, if this is a factory or a building or a city or a bridge, doesn't matter, will start to make use of ICT technologies like IoT, system of systems, cloud, data analytics, whatever you want to call it. The OT, operational technology, is still SCADA, DCS, PLCs, and so on and so on. And there is both technology and cultural gap between these domains. Just as an example, so Terminal 5 is, whatever, 3, 4, 5 years old now. It actually has 5 million connected points. Interesting number. But this is made in, I don't know how many different control or monitoring systems, which means that we can find doors in Hereford Terminal 5 which have a number of sensors, each of them checking whether the door is closed or not. But the signal goes to various control or monitoring systems. And these systems are not connected, they are not integrated. And this is just how it looks like. If we look at current SCADA DCS systems or monitoring systems around the globe, we basically don't find any ones which are larger than 100,000 instrument sensor points and so on. I've spoken to maybe Steven Schneider, etc., and we roughly find something like 5 of these systems around the globe. There are still people who haven't muted your microphone, so please help me in doing so. I hear people typing. Let's move on. All this integration has been looked into by various industries. This is just an example from process industries like steel plants or mines or paper mills and so on. And they are very much integrated to which is then supplying heat to offices and so on. They need, of course, the raw material and products. And this is a simple picture where people now start to understand we need to move these things together to be able to leverage on the information that's provided in kind of each of these 5 players that we see in this picture. There has been investigations from a number of companies, and you can find long lists from various players who is telling where is the money, what's the benefits. We can also look at what Artemis recently put out as a report on the market growth in various areas. And this is kind of the value chain of the electronics components and system community. And it's pretty clear that we have nice figures of growth on components and tools and so on. But for the system of system, when things start to fall together, the growth numbers are larger. On the upstream side, we have about 2 times, but on the downstream side, we have 10 times more over a pretty short time period. So this is the drivers behind why this is moving. So please again, try to mute your microphones. That will help all of us to get a reasonable sound quality. So this is the kind of drivers we see behind. What about automation system architecture, and how does it look like in reality today? We very much rely on the existing ISO 95 architecture for automation in industry, whether this is the operation of a bridge or a paper mill or a car factory, doesn't matter, all of them are based on the same technologies. This is the ISO 95 pyramid, and it's the current production automation state of the art. It turns out that these pyramids seem to be very rigid today. They actually provide very nicely working automation, but also the automation, when analyzed, is very clearly inflexible. Although there should not be cross-layer dependencies, these implementation has evolved over years. So yes, there are cross-layer dependencies, which is creating additional inflexibility and rigidity, and there is basically no security at all. For the implementation of these, we rely on heterogeneous and incompatible communication networks. You will find normally something like 10 various communication protocols in most factories. And the most common one is still analog 4 to 20 milliamps. Students at universities, they don't learn this anymore. We will find a shortage of competence for these technologies pretty soon. The discussion that has been around is to move this then to cloud or to internet technologies, integrating this with the ICT word. And this is what people are trying to do, and this is where we start to need some type of platforms or frameworks that can support us in doing that. And this is one of the very basic drivers for why Arrowhead and Arrowhead Framework was created a couple of years ago. It's also interesting to see that we have these new architectures, which are beyond ISO 95, RAMI 4.0 from Germany, and the IIRA from basically US. They are different, but they are kind of emerging nowadays. The RAMI 4.0, well-known picture for most of you, I think. And we can see that the ISO 95 is basically on the lower right of this architecture. This is drawn as layers, but we should think of it as a continuum. That's how it in reality will work in the end. The IIRA is also drawn as layers, so on, but again, both of them points out that this is not a layered architecture. It's a way of describing the word that we have to operate in. So this is somewhat where we are looking forward to from a production, operational viewpoint, business viewpoint, functional maintenance viewpoints, etc., etc. This is not technology implementations, but this is the desires from the higher views on how we can get efficient. So we see something that the automation technology transition, and this is also where we going to see digitization very much, that there is some type of a migration path, but the left-hand side of this picture will live for many, many years. Control systems tend to be pretty old. We do have examples of working control systems which are, or automation systems which are built in the 50s, so they are 60 to 70 years old, based on relays and so on. So it's an interesting word. If we look at these new architectures, the digitalized industry, we are looking forward to something which is a dynamic digital industry, that we can make changes to the production and to the automation system in runtime, and that we also can be exposed to messages we need to communicate with other players, other stakeholders, and that will require a lot of security thinking as well. So, and we will see that everything will be based on internet technologies, so IoT based, and that these have to be interoperable. But we also need to look at various management situation in a much more detail with these new architectures compared to what we have done before. So functional management, security management, business management, logistics management, safety management, etc. So how do we move them from SCADA, DCS to Internet of Things and System of Systems? There has been some work done on this, but let's just give you some definitions. I don't know whether everyone really know these names. SCADA is actually supervisory control and data acquisition, and DCS is distributed control system. And the big players supplying this is Siemens, ABB, Schneider, Metso, Valmet, Emerson, Honeywell, etc. And normally it ends up with big figures like this, where we have the control of a lot of things with sensors and actuators at the bottom of the picture. We have these DCS systems in the middle, the red circles. We have PLCs in between here, between the SCADA, DCS and the sensors. And on the higher levels, we have operations monitoring, and we have further development of these systems and so on. SCADA and DCS systems, they rely on thinking that they always ask for data. They are so-called pull-oriented. So they are scanning the sensors and actuator points that they are connected to. They're scanning the items. Anyone had a question? You do you have a question? No, then we mute him. So in these systems, we are pulling data on a regular schedule. Some loops need 1 millisecond, others 1 second, 10 seconds, and so on. And this is a design time configuration, how you do this. If you change these schedule times and so on, you need to start to test your that the DCS or the SCADA system actually can meet all these again. Otherwise, you're going to have problem with some of the control loops involved there. And this is kind of a historical situation. From the beginning, when we started to see the SCADA system, they were monolithic, centralized. Then we started to distribute these, and the second generation, this is why we got the term distributed control systems. Then they started to be networked, and what we are into now is to see that these will all live on some type of internet environment where things are connected, and we are controlling who is allowed to talk to who with security policies, operational policies, orchestration policies, etc. So we will move from these solutions to where we have IoT stuff involved at certain points within a picture like this. And this is the migration that we will see that many are right in the middle of, and this is not super simple. Just to give you an example, we did some of this work together with a couple of companies. These are slides from Midrock, an integration company that operates mainly in Europe. So this is a SCADA DCS system taken from a mining company, LKAB. And then we made an idea of how to move this DCS system to an IoT system view. And there is a number of steps in here, and we'll just flip these through. So this is some of the very first approaches how to do a migration like this. And this can be a process over several years to actually do this. So first of all, to move, get us some infrastructure where we can start to accommodate the information from the classical DCS setup. And then what can we move first? The higher levels, which are non-real time, we can move them first, and we can find certain places where we can break out this and say that, yes, this we can make as a local ICT-based situation, which we can connect into the old existing infrastructure. And then we can go on with this. We can find other things which are less sensitive, and where we can learn how to move various places into the cloud on the right-hand side. And in this way, we can go on, and again, we can take the higher levels much more easier than the lower levels where we have the control systems right now, and where we have all the sensitive connection to the physics and with real-time dependencies and so on. And this is how this can be done. We have made these type of operations in a project called IMC ASOP a couple of years ago. We made it together with a mining company, LTAB, the Europe's largest iron ore mining company, and looking at their pelletization plants in Kiruna. And we were looking at particular, what you see in the middle here is a frame around this big tube. And this is basically a bearing, one of the most sensitive bearings that's in that process. So if that bearing breaks, they will have a major breakdown and a major stop of the production. So there was a lubrication system connected to this, and we were allowed to actually implement that as an IoT system, a system solution instead of the classical PLC. And then we made that. We took that lubrication system, and this is how it looked like. There is a valve. There is an air-operated, basically drum, meaning a pump. There are some other valves, and there are some air supply that is connecting to this. Doesn't look fancy at all, but this is how it looks like in real operation, and it works. This is the logical description how this is connected, and there we also see the connection to the DCS system, and where there is the PLC that is actually controlling the various parts of the lubrication system. We were then allowed to build a service-oriented architecture, IoT-based situation to execute what the PLC did before, and where this now is made in a much more distributed way. Here is a brief architecture of how this was done, and we had a number of wireless. Something happened. My presentation died, so sorry for that. Just let me restart things. I think this is where I was. So we had a number of wireless sensors. We had connection to an ASI bus, and we were able to integrate all these cameras up to the DCS system. So I hope you see my slides again.
Yes, now we can see them. If you can make them big.
Yep. There we are.
Good.
And we were allowed to run this for 6 hours in operation. And we went through all the field acceptance tests and everything that LTAB do with any other automation systems that they are requiring. So we have done the full story with an automation system using IoT system as system. This is kind of the starting point where we started to be able to make real solutions using service-oriented architectures and IoT and so on. This is way back in 2011 or 12. There is a movie of this. I will not show it, but you will get the slides and the PPT, so the movie is embedded, so you can have a look at that and what was done there. It's a few minutes, but we will not spend time on that right now. But it will be available with the presentation and the slides. Oops. So if we look at current trends in automation system, what's going on and what's the changes we see? There are some roadmaps. Roadmaps from EFRA, from Germany, Industry 4.0, and there is also a process IT.eu a grouping around process industries that has made quite some nice roadmaps. If we do the analysis of these, they are pointing very much in the same direction, and points at various parts where we need to really improve technology to actually exploit the benefits that people can identify. And some of these roadmaps, they are both give ideas about benefits, but also the technologies and the paths how to build it. If we just take some keywords from these, we see lot size one production, real-time, on-demand production, raw material yield, multi-stakeholder operation, real-time, big data analytics, one-time automation of production changes. But we also see the situation of cyber war, criminal blackmailing, security holes that will impair safety, and that large system automation solution. They still need to be safe for human society, infrastructure, and so on. And that we know that criminals and states are already testing these things. A couple of years ago, the oil production in Nigeria stopped for a few days. There was someone testing to stop the operation of all the computers within a couple of companies there, and this is going on. So this is where we are, and you all know about Stuxnet, and there is another nice movie on this, and it's worthwhile looking at to understand what's going on. This one is from 2011 or 12. Yeah, the movie is from 2012. But Stuxnet was founded in 2011. It's important to get a feeling for what can happen. So if we look at, I would not spend time on looking at the movie. You can do that yourself. Future automation requirements. What do we have? So it's very clear that we have digitization automation requirements, and we very much have the same requirements as ISO 95. We have real-time performances, we have engineering simplicity, interoperability, security and trust, safety, scalability, system-of-system integration, flexibility, and all these kind of keywords are there. But we still need to remember that doing things with IoT, ICT technology will not take away the requirements that we have on the OT side as of today. And not written here, but of course, robustness, 24/7, 365. Many of these factors are continuous working systems, and this is very, very important. So even updates of automation system becomes very critical operations in production of various products or services. So robust hard real-time, we can say this is not possible over open internet. Open internet doesn't have these real-time possibilities that the current automation production has. I was in a meeting with Ford a couple of years ago, and they were demanding 4 milliseconds at very, very large parts of their production lines. And we cannot do 4 milliseconds with tens of thousands or hundreds of thousands of IOs over the open internet. So we need protection. We need ways of protecting these control loops, and ways of doing that is self-contained networks, which kind of a SCADA DCS system actually provides. We need firewalls and so on if we're going to run this on ICT technology. And we also need real-time capable physical and transport layers like industrial internet, But we also need quality of service monitoring and possibilities to control and tune the operation of the network as such. Another thing is this engineering simplicity. Of course, the customer is buying something from an automation company saying that, yes, this is the result of the automation that is the interesting part. So it's the application focus that we want to put to the engineering. But if we do analysis of the engineering costs for automation systems, and we can find a number of these analyses, but I took some data from the previous Arrowhead project, and companies here came up with numbers saying that the application, the time spent of building the application was actually 20 to 35% of the total time for building the solution. Connectivity was actually eating the rest. How to make things talk to each other. So the important thing seemingly here to reduce engineering cost is to remove lower layer complexity from the engineering process, and that we can have machines to solve these things on their own without the need for human engineering efforts to be involved, and does both be costly but also creating time lags because humans are not available right out of the box every second we need. So we need some type of interoperability of IoT technologies, and there are certain, we need them to talk the same physical layer, we need them to talk the same protocols and transport protocols and so on. Most of these things can be solved and is solved, and Arrowhead is actually handling this up to, or Arrowhead Framework is handling this up to the service protocol levels. But there is one area which is still a big non-interoperable area, and this is when we start to talk about data. Data and their semantics, and there are too many. I wrote 100,000 various data structures and semantics. We can probably multiply this or qubits or something like that. That's where we're going to end up. And this is the very, very big interoperability problem. There is not a lot, but there is clearly research going on in this direction, and people are dealing with ontologies, natural language approaches, machine learning approaches, and we do have people in the Arrowhead Tools project and in the Proactive project that is looking into this. But it's still an open area where engineers still need to be involved, otherwise things will not work. There are other things that's necessary. We need to handle security. Who is allowed to talk to who? We need to authenticate hardware, software, and the services. We need to authorize who is allowed to get what data and maybe what part of data. We need to do some accounting on that. We also need to know have we the right hardware onboarded to our implementation? How do we handle software? How do we protect the payload? And how do we manage all this security? How do we assess that we are that the implementation is actually in line with certain standards that we like to adhere to, and so on. We need these things to be scalable, and it's very clear that digitalization is pushing for integration at a much larger scale than what we can do today, way beyond the 10 to the 5 connected IoTs that current SCADA DCS systems is capable of. But we still need to preserve all the requirements that current SCADA DCS systems is capable of executing. So like real-time functionality and so on. So the next generation automation and digitization technologies based on IoT and system of systems, how will that look like, and what do we see right now? It's very clear that I would say almost all approaches we see today are based on service-oriented architecture. There are some approaches using agent technologies, mostly academic so far, and there are very many solutions built in industry where you actually hack together a piece of code that actually is fixing the communication between various machines and devices. This is the straightforward, quick solution to do it today. But every time you need to do some changes, you need to probably rewrite that code or get some new code since the old code is not executable on the new hardware and so on. So the service-oriented architecture is the leading approach to support us in doing this. And just some brief on what is service-oriented architecture. And in general, this is about data exchange between one entity that is producing a service and another entity which is consuming a service. And this is normally a small software system that resides on any hardware. It could be a sensor, could be on a general computer, or could even be on an Amazon cloud. So in this case, it's a service producer. It could be a sensor that is then producing a service with an interface where the data that's coming over to the consumer is the sensor information, for example, the pressure data, which is then used in maybe an analytics algorithm for checking whether we want to make an alarm to a driver or that it's used in a controller or something like that. There are a number of properties which is important for a service-oriented architecture. It's called loosely coupled, that we don't need to tell who's going to talk to who until we are running, and we can change that in runtime. But in this case, it's important that we can discover what's there, that we can make a discovery of which systems are available, and that we then can make the connection in runtime. Anyone have a question? No? So this is just a simple diagram how this can be implemented. And normally we have some type of service registry that is helping us with this discovery process. So every producer of a service have to register itself to a service registry. And then anyone else can go there and ask what's available. And then we can initiate a consumption of that service. That's a fundamental principle. Late binding is this situation where we can tell who should talk to each other, and this process is normally called an orchestration process, where an orchestration system is telling that yes, system A going to talk to system B or whatever identities they have, and then we automatically can provide the endpoints for a computer to actually, for the microcontroller in any system or a computer to find the location where to ask for that service. And of course, here we need to think about security. So the authentication of the consumer and the authorization of this consumption also has to be considered. And this is how it may look like in this case. So first we have the service registration situation, and then we have the orchestration that this one is telling this consumer here, the application service consumer system, to actually, this is the endpoint, this is the network endpoint where you will ask for the service. And then the application provider will then check whether the consuming partner actually is authorized to consume this data. So security is there, and in this process we both authenticate, checking that the consumer has the correct keys and certificates, and so we can identify the software system there, and then we can also identify that this software system has the authorization to consume the specific data that is produced. So we are then creating what's called autonomy, which means that in the previous picture, once all these, the blue, the green, and the red system has been consulted, the two application systems can run basically in isolation on their own. They don't need the others. There might be a situation where the authorization system might be needed if you want to authorize every consumption of the data. But in general, this is how we create autonomy, and once this is set up, it will execute, and then we can change things in runtime by changing the policies for the orchestration system and the authorization system. So this is very important properties that we need to understand, which is very different from how current SCADA, DCS, and PC systems are working. And this is one of the kind of learning barriers that we need to have some knowledge of that. Other SOA properties is that here we can now implement easily both the pull, exactly as the same as the SCADA DCS systems, and a push behavior, meaning type of a subscription to data if something happens. So if, for example, the pressure, where a pressure sensor is reading the data, when the pressure is changing to higher than this example 2 bar, then data is pushed from that producer to the consumer. And that means that we are reducing the load on the network that we're connected to. And of course, we are reducing the energy consumption as well, since communication is expensive. What do we see then? That if we can build these service-oriented architectures and so on, people have provided a number of service-oriented protocols like CoAP, DDS, XMPP, DPWS, UPnP, MQTT, OPC-UA, REST, and so on. But if we see what is people trying to do, we find many situations where there is an application that is talking a certain service protocol that need to talk to another one with another protocol. Can these two talk to each other today? And the answer is no. They are similar, but they are for sure not the same, and this will need some type of translation, and this is what Arrowhead Framework today is capable of providing. Most often, you see that people say that yes, we did say that you need to define a lot of things, that we only use CoAP, we only use a specific data compression, we use a specific semantic and encoding and description of this, and then we can talk to each other. But this is not the case in industry, and will probably not be the case over time. So we cannot rely on that everyone's going to do as I want it to be. It's just to look around, and we have various requirements, and we like things in various ways. So it's both technology, political, and what people actually is knowledgeable about that will decide what will a certain player have to implement and so on. So just to summarize this part of my webinar, automation will integrate many folders. These large automations and digitization systems will consist of very large numbers, and it's clear that current standards are not sufficient. The system seems to be able to implement the advanced proposed architectures like RAMEC 4.0 and industrial internet reference architecture. And that the preferred technology today is service-oriented architectures, and that we have a couple of things which are key to actually make this working. Ability that we can integrate these things, that we can migrate from legacy, and that we can have control over the data that is produced. Anyone having a question so far on this? Let me then move on to the next part of this. So I will now talk more on what we call local clouds. And this is an approach on how to provide security and enable real-time things, still using only ICT technology, IP technology. And this is again very fundamental to how Arrowhead Framework is designed and what are the benefits that this is actually giving us. So the local cloud concept. You've seen this before. So we are moving here from the existing implementations, lower left, to implementations on the lower right. And in this case, we talk about local automation cloud implementations. And we have the requirements with real-time, safety, security, scalability, and so on. And if we then look at the global cloud approach, where this global cloud might be Amazon or Microsoft or whoever, then people are trying, and there actually is some control situations going on where we are sending things to cloud solutions somewhere else on the globe. But it's still clear that we are sending data over open internet, and we can never guarantee the real-time situation. And we are also, even if we have encrypted data and so on, we are exposing ourselves to a situation where people can start to listen to what we do and redirect and change the real-time performances, the latencies, and so on, which is totally out of our control. So this is probably not the most feasible way of doing this. What we did was then to look at automation in general, and most of the digitization is pretty local, geographically local. And that said that can we work with what we call then local clouds, and we here should more look at these as shells, where we actually make a protective shell around the technologies, the control that we want to protect. And that means that we have a protective fence against any communication, external communication. If we look at normal factories today, the fence is around the complete factory. And it's very clear that current fences in today's factories are not very efficient. I quite often get answers like, to questions like this, how do you enable that a supplier actually is able to update this PLC or this system, which is a very local situation in a plant, in a workstation. And very often I get the answer, there is a back door, so they can get in remotely to do these things. and all these backdoors are so the protected fence is leaking. It's a leaking, a very leaking fence. But the approach we do here is that we move these local clouds down to like factory or workstation level, or even smaller around the important control loops that's necessary to protect from a production viewpoint. So in this case, we can make cloud environments where we really can do hard real-time controls and where we can protect all this interconnection and automation digitalization that's done there from any other communication in the factory or external. So it's a way of protecting sensitive operations as real-time cloud scope control, safety critical operations, etc. If we compare this to the cloud situation, here on the y-axis we have clouds on the top. We have edge and fog, which Ericsson and Cisco is talking a lot about, where they think that they can provide their cell heads and their routers as computational units. That was their first ideas to this. And when I'm talking about local clouds, this is what we do, clouds to the physics. But we can even think that these clouds can go up to the fog edge level. You may even have the support by Microsoft, for example, in another cloud on its own. And the important thing is that we should be able to communicate between these clouds in a secure way, but we will lose real-time performance. So it's a way of building local private networks where we can protect these sensitive cyber physical system operations. And once that's done, we can ensure that we can build share data between various parts of a factory or an installation, and this can be basically any level. So there are a number of properties that we give to these local clouds, and I will not go into details on all these, but one of the most important things is that it's self-contained. It should not need anything from outside to actually execute its intended operations. This is a way to provide a strong security fence to external networks. So there should not be any other traffic on that local private network that we have there. And in this, we should also then provide interoperability between those entities, those application systems that we want to provide there. And these local clouds should provide inter-cloud service exchanges. But in this case, we will certainly lose real-time, but these inter-cloud service exchanges need to preserve the security policies set forth in each of the local clouds. So,
Jakob?
Yes.
Christina speaking. I have a question. You're speaking about these local clouds, but I don't understand the difference between you intend to do and what is actually the situation. That, for example, in the companies there are these private servers, private clouds, and also in Infineon we have the security. We have not just for XML, but we can communicate between different sites and so on. So, which is the difference between these? Perhaps I lost something before, but for me, you are explaining something that actually is already existing. was my understanding.
As I said a few minutes ago, when we start to analyze what's in a factory, might be Infineon or Volvo or no company name, no forgotten, we will very soon find that, yes, there is an ambition to make this protected, but once you come down to operational technology, it is not protected to a very large extent anymore.
Okay.
At the IT level, yes, there is protection. But once you get down to operational technology, you start to lose these protections.
Okay. Thank you.
And if you go to LinkedIn, you will find huge discussions on how to protect and how many attempts to actually break into SCADA systems that's out there. This is a well discussed but not solved problem as of today.
Director, may I also ask a question?
Yes.
Concerning the previous slide about the local cloud properties, because written that it was supporting inter-cloud services and system of system integration. So I was thinking that one of these clouds actually could be say third-party cloud that we equip with a gatekeeper in such a way that we can integrate in this way, say the Arrowhead pure local cloud with other clouds that are third party, but they are interfaced through the gatekeeper. Is this correct?
Yeah. Yes, this is perfectly correct, and this is a way of interconnecting data between a subcontractor and a customer, for example.
Thank you.
So this is something that we know that in the Arrowhead Tools projects we have, I think there are two use cases. How do we share data with subcontractors in a secure way, exposing more data than necessary? And how can we build these solutions in a very efficient way? So the question is highly relevant, and these are examples that people are packing today, and most cases these are built using some type of middleware and potentially some cloud solutions offered by Microsoft or something like that. But then data is also kind of exposed on the internet in a way that may create other problems. So coming back to the technologies, and again, what have we used when we built this Arrowhead framework based on all these kind of background and which are the requirements? So it's service-oriented architectures. And you see in this picture that this is how we want to communicate between two entities, whether this is a control loop or whether this is a subcontractor that is requesting data from the customer or the other way around. So important with these local cloud, they are self-contained, and we need some few resources to establish this local cloud. We need this service registry, and for extended security, we want to know which are the various software systems that reside in that local cloud, and we want to know which are the hardwares that's actually in that local cloud. We need a way of telling who's going to talk to who, so an orchestration situation, and we need something that is handling authentication and authorization. So this is not very much, but we certainly need this to be able to have the properties we are looking forward to. So for the security, we need a closed detached network. no external communication. And we need the authentication of service consumers and, of course, the producers as well. But the authorization of a service consumption, and we want to have an accounting of service consumption so we can have logs on what has actually happened, which means it's a possibility to analyze whether we have a break-in of someone that is doing things which they should not. We need interoperability within these local clouds. We need interoperability at protocol level, data semantics, the encoding, and at the service level. But the big trouble here is the semantics. All the others can today be handled by machines, and Arrowhead tools is one of the Arrowhead Framework is one of the pioneers in actually providing protocol translation and SOA protocol translations. And we need something that is telling who going to talk to who, and orchestrating these interactions, these service exchanges. And are they a pull characteristic? Are they a push characteristic? So we can handle that. Then we will be supported by a number of more things that can help us to build these. So can we design and build these automation systems based on local clouds with some design support, configuration of individual software parts and hardware parts, deployment, operation and maintenance, and so on. And for this reason, Arrowhead is providing a number of support core systems, we call them. We also need a way of saying what is actually allowed to be within this cloud network. So we need a secure local cloud deployment procedure, which is very called an onboarding procedure. And this may be as complex that we have a security controller in the hardware where we can actually ensure that this hardware actually is a hardware from, let's say, Schneider. And we know that both Infineon and NXP, for example, do have these security controllers in the market. So these processes, we need to enhance our security situation. This might also be necessary for very safety critical operations of certain things that we know exactly what is the hardware that actually installed on that aircraft or in that critical part of a factory. So it's very clear that we need an inter-cloud service exchange capability, and that we need this to be part of the same security schema as what's inside each of these local clouds. So how do we create this? Can we establish such a local cloud, and what is necessary? First of all, we need a service registry. We spoke about this a couple of minutes ago. So the producer have to register itself into a service registry, and then we can discover that this service producer is available on the network, and then we can find the endpoint, and then we can go and ask for that interface and what the data that interface is providing. So this is a simple control loop where we have where we have a sensor that is producing data, which is consumed by a controller, which in turn is producing a set point for an actuator, which is then consumed by the actuator as such. And we can build up then control loop orchestration, where the sensor is then requesting an orchestration where the control system is requesting an orchestration. Where can I find the sensor that I want to consume the data from? And the orchestration system will actually then provide the endpoint of that one. And the same thing then for the actuator that will require the orchestration, request the orchestration, get the endpoint, and then subscribe, in this case, to a control event. Once things have changed sufficiently, then we get some new data. And after that, we don't need the interaction with the orchestration store, and we can then have these two data consumptions to work in an autonomous way. And internally, in local clouds, the security, we look forward to basically three important things. One is that we can authenticate the service consumer, and that we can authorize a specific consumption of the service, and that we can encrypt the service data. These are important things within that local cloud. And how we do this is that when you then have a system A that's producing a service, we request a service registration, and then the service registers actually can check with the authorization system whether this service actually has the rights to be in this network, and we can deny it. And this is just a simple example of how these authorization situations can be used. This will enable us to build local clouds, and the minimal local cloud is basically then the service registry, the orchestration system, and the authorization system, and at least two of these application systems. This is the minimum we need, and we don't need a lot of computers to actually execute these core system, or mandatory core system, we call them. This can be run on a Raspberry Pi easily. That size of computer. We don't need a lot of computing power. We don't need a lot of memory. So this is light-weighted, clearly light-weighted. This is a graph of the basic local cloud service administration. All these dotted lines here is the administrative phase of setting up the consumption of data from the controller to the temperature sensor and the air fan from the controller. And once the dotted lines has been accomplished, with the lower level, the solid lines here can run as long as the authorization and orchestration actually allow them to do so. And this can be changed, stopped in runtime, and if the temperature change sensor is changed for a malfunction reason, the new one will put itself into the service registry. The old one will be deregistered, or the orchestration system will find out that this one is not anymore available. You can then just find a new one and say that, okay, run with this one instead. So maintenance can here be much more simple than we can do it with SCADA easier. And it's also very clear that one hardware, there's green blob here is one computer, could be a multi-core machine or whatever, and that we can run many of these application systems on one hardware. And this is exactly what we, for example, do in these Raspberry Pi that works as some type of a local cloud head. But we want to know which are the hardwares and which are the software systems that are actually installed. And this is why we also request to have what we call a system registry and a device registry. This is, again, important from a security, but also from a quality of service viewpoint. These are not mandatory, but can be used. Depends on the overall ambitions and designs and the cost levels and so on. So how do we support automation engineering? How do we do that? Currently, there is a number of standards for doing so: ISO 95, ISO 99, IEC 81346, etc., etc. And the new ones are Industry 4.0 standards, ROMI 4.0, and IIR. The new ones, the engineering standards, are not kind of covering these new standards. That's very clear. So we need to be able to handle what's at plant level or a section of a plant. We need to be able to understand which are the devices that have to interact. What are the devices? What are the functional levels? And so on and so on. Our approach to this has been to provide what we call a plant description systems where we can capture data that currently is produced by engineering tools that is used already in the ISO 95 work, but we can bring these things together. But the additional things which we are here after is also to be able to create these orchestration rules. Who's going to talk to who, and how can we extract these orchestration rules such that we can bring these into the machinery that we can have this to work with a less need for engineering and operational staff. So here's a simple example how this can be captured. This is the controller for keeping the level in a tank, and we here have the various hardware involved, and the brown colors now should be taken as the blue colors in that figure. We've never fixed these colors, but this is how it is. So these are the physical, and we know where they are connected. The yellow ones here are the orchestration. These are the orchestration rules, the connections that need to be connected. We can then redraw this picture into a plant description situation. These are the hardware, and these are then the service connection, the orchestration rules. That's the yellow lines on the previous slide. So these things, we can start to capture these things and be able to move these information into the orchestration system. And this is a necessary step, which is currently beyond what's available on the market today. But Arrowhead Framework is providing support for this to, I wouldn't say everything is fixed, but to some extent this is provided already. We need to be able to configure devices and software systems, so we can, for example, provide new control code to a PLC functionality, or handle the sample rate of a sensor, or if it should sleep, what are the sensitivity it should use, and so on and so on. If you take a standard flow meter, there might be currently 100 configurations possible in a normal flow meter today. This is necessary. We need to do audits, so we need to be able to store data. What is actually going on? What happens? So we can do analysis both in real time, but also in kind of a situation where if something happened, can we analyze what actually happened? What happened we thought about in the interaction with the physics? There also might be situations where we have very simple producers of data, which might be a very tiny system, but there are quite many that need that information. So we need a way of offloading low resource data producers, then we created something that we call an event handler that actually can support us to reduce the load on a tiny data producer, and then we can go from just a pull situation to a publish subscribe situation on the other side. These are support situations that we like to provide. We like to provide quality of service, so monitoring real-time situation, provide support for changing the networking in a way. If we're adding more things into a local cloud, we can say that yes, this is possible or not possible. And we need a secure inter-cloud service exchanges. So we need to actually, in one way or another, open up a hole in our local cloud shell and to provide a data path between application systems, and this needs some support. And in the Arrowhead Framework nomenclature, we call this gateway and gatekeeper. So this is the principles about local clouds and what's necessary, and what we see as important. I will now switch to a third set of slides, and we'll go into the final parts of this. Anyone having any questions so far?
Yes, if I may.
Sure.
One question about this quality of service. There was a point stating that there is a certain need for assuring that the message is delivered. What happens when some register is registered by the service register, is orchestrated, authenticated, and after some time it stops responding? There is some system responsible for detecting such an event?
Yeah. There are mechanisms in the service registry to actually check whether the registered systems are alive or not. And there are two approaches to this. This is a few years since we did this, so my memory might slip right now. But there are two approaches. One is actually to have some type of keep alive situation. And then if something is not kept alive, it should be deregistered. And the orchestration system then should have some time frames where it should go and check, is my orchestration still valid? Are the stuff that I orchestrated still there? So that's on the other side. And the general rule is that a system that registers itself should also deregister if it's taken down in a proper way. But of course, that will in many cases not happen. And the other approach is that re-registration should be required from these application systems, meaning that there is a lifetime of the registration.
Okay, thank you very much.
Okay, let's move on to itchy-bitchy details, and now we talk about the architecture. You can still see my screen, I hope?
Yes.
Yes.
Very good, very good.
Yes.
I would also have a question, just whether my basic understanding is correct. So actually, we were experimenting a little bit with up to now only the insecure things to keep things simple. And so my basic understanding is that for each request a consumer makes, it will actually first trigger this orchestration process and then receive in the end of the registration process, it receives the payload with a REST endpoint where it actually can access the provider. And then in the second step, it directly makes the request to the provider. Is that correct, this understanding?
Yeah. The
Okay.
implementation of the orchestrator is actually such that the orchestrator now checks with the authorization system if it can authenticate the consumer, and if it can get an authorization for that consumer to actually consume a specific produced service. So it will get both the endpoint and a token that the producing service then can check with the authorization system whether this is valid or not. And if it is valid for an infinite time, they just go on. It would be valid for, let's say, 30 minutes or for 10,000 consumptions or whatever.
Okay. And what about the overhead? I mean, the overhead of the orchestration process can be a problem, or how can we make sure that?
The orchestration process is only involved during the setup of the consumption of a service. Once this is done, that the consumer has the endpoint, it can go on without the involvement of the orchestration system.
Okay.
So we have an administrative phase of setting this up, and this might take a couple of seconds to do. And once this administrative phase is done, the consumer can consume the data from the producer without any involvement of the orchestration or the service registry systems. And there might be an involvement of the authorization system, but this is dependent on the security policy.
Okay, thank you.
Can I ask a question as well?
Sure.
So I do not have a full understanding of the orchestration process. So if I am a consumer and I need a certain service, I need to consume a certain service, can I just go to the service registry and see who is providing that service? So what is the orchestration giving me more than that?
Yes, an individual application service in theory can go to the service registry and find out, this is what I want. But that means that you need, for every application system, you need to kind of provide this information in design time. Saying that having the orchestration system provides you a mechanism where you actually can create a number of these orchestration rules telling that consumer, whatever, call it or something, needs to find, we should have pressure data for that one. Since that's a control loop or an analytics of something. And then from an engineering perspective, we see that there are 5 points of where we can get this pressure data from. It's sufficient to have 2 of them working. And that means that the application system don't need to know at design time which are these 5 systems that it can consume the pressure data from. This can then be captured in a plant description, which is then generating the orchestration rules, which is then pushed down to this application system, Robert, and giving it 2 ones which for various reasons seems to be the most appropriate from a higher level engineering information. And this we can change in runtime. But if you have this hard-coded in your application system, yes, it will work, but you cannot change it easily in runtime.
That's much clearer. Thank you so much.
Good, good. Okay, so now we'll dive into the architecture and some nitty-gritty details and definitions, so we will be more and more detailed on this. So quite a bit about the architecture fundamentals and how we actually implement this based on the requirements and the principles we have been discussing in the previous 1.5 hours. So the objective of this is to facilitate the creation of local automation clouds. And again, this loosely coupled late binding and lookup is what we really want to do. We have, from a computer science perspective, what we call an information-centric networking thinking. This is what people at IETF is discussing and trying to define in various RFCs. And it's also important to see that a system that is producing a service, initially, actually, it owns its own data, but this can be provided the authority to someone else. But we thought we needed to have such a definition. And that what we call information assurance shall be at the service exchange level. So this is where we can authorize the service consumption, where we can authenticate the consumer, and where we also then have the capability to ensure that we have proper encryption of the data. We should allow for publish-subscribe, meaning a push approach for pushing data based on some criteria, and we should, of course, then be able just to ask for data on a time-based approach, for example. And we also want to have the possibility to dynamically create new services and its subsequent usage. The subsequent usage is, of course, this orchestration that we just discussed based on the question here. But we should also be able to create new services that necessary, so we can instantiate, for example, new copies of a service that is needed for one or another reason. So the architectural design is in a way that we have a minimal set of what we call the mandatory systems and their mandatory services and their systems to create this local cloud, and a set of automation support services to facilitate the design of automation digitization solutions based on this IoT and system-of-system approach. So I do have some definitions, maybe boring, but still I think it's important that we speak about a similar language and we have a similar understanding of some keywords here. So Arrowhead Framework has defined a number of keywords and based on service, system, device, local cloud, and system of systems. And let me just walk through this briefly. So a service, we have discussed this previously. So this is the exchange of the information. That's the service. And the service is produced by a software system. And the service can have associated metadata and things about non-functional requirements, real time, and so on and so on. And what to be a compliant service, that it should be possible to register into the service registry, and it may be capable of being dynamically configured. A system is a tricky word, but yeah, we use it as well as many others. So a system is a piece of software that actually provides or consumes services. So this is a piece of software that is implemented and executed on a hardware device. And these systems can also then have associated metadata for example, which is the version of the software. And there is a number of requirements for being compliant in this case. A device is a piece of equipment with computational memory communication capability, which hosts one or several Arrowhead Framework software systems. And it can be bootstrapped or onboarded into an Arrowhead Framework local cloud. Yeah, this is the same stuff there again. And the local cloud is a self-contained network with at least the 3 mandatory core systems deployed and at least 1 application system deployed. This is the minimum, absolute minimum set of doing so. Compliancy here again. But what is the system of system then? Mandatory core systems and exchange information by means of services. So a local cloud is then a system of system in this context. And 2 local clouds is just a larger implementation of a system of system. And this can end up in pictures like this, where we have 2 local clouds where we actually then have a communication between application system E and the application system C, and here is implied as gateway gatekeeper situation between C and A, and then the data can go to the application system B in a completely other cloud. And this can of course be located somewhere else on the globe as well. The individual local clouds are local, geographically local, but between local clouds we can have on different parts of the globe. That's the technology allows perfectly for that. How do we think about documentation around this? We have a documentation structure where a software system is described with what we call a sysd document. And there is a black box and a white box. The white box is called sysdd. The system of system is for what's going to happen within or between various local clouds. But if we take a system, it will expose some type of services, and it has an interface description. It has a service description, and this interface description is then also having a communication profile and a semantics profile. And in this interface description, we are telling how does the interface look like, which are the data structures, and which are the interfaces that we actually can ask for something from that service. And the service description is then providing the higher level description of what is it actually providing. But the details is in the what we call the IDD document. And this can then be connected to an engineering procedure in the following way. I took some parts of providing the engineering process. So this is the requirements, the functional design, the architecture, the actual procurement and engineering, and where we will find the various documents from the Arrowhead Framework documentation structure. So on the requirements part, this is the SOSD. The functional design and the actual architectural implementation will be the system of system design documents. And then for each of the systems, we will have system design documents, and for where we then have which are the hardwares that will be involved connected to the procurement process, we will go to a system of design description, and then the services, the service description will be there, and then finally the interfaces will be there. So we can connect this to a pretty normal engineering process, so we can see where will each of these parts be documented and how can we make use of that. We can of course then use like SysML, UML tools to actually make these documentations. There is quite a nice paper that soon will be published on how this can be connected. And we also need to identify these services, systems, devices, and local clouds. The approach we are using is basically connecting us to what Internet is using very much, so DNS and DNS SD, which is basically comes from Apple. This is an extension of the Apple Talk protocol a long time ago. But it works pretty nice and it scales fantastically. So this is the fundamental principle we like to do. We know that we have a bug with DNS SD which hasn't been resolved yet. So there is also an implemented version where the data structures, these namings and so on, are stored in an MySQL database instead of the DNS SD structure. There are two classes of services. There are core services, mandatory core service and support core services, and there are application services. So it's trying to keep this to a smaller number. But how do we identify these? So core services, they have a service name and then they have a service type. And here we have this AHFC, Arrowhead Framework Core Service, and then the application service is _AHF service type, and then we tell what is the protocol, which is the transport, and what's the domain. And this is exactly a copy of the structure that's used in DNS SD standards. So we're very compliant with existing Internet standards. And if we bring this back to the description documentation structure, we can see at the top level where we're talking about the system of system. This is where we provide naming for local clouds. The system levels, this is where we provide naming for the system and device and the device. And then at the interface, this is where we provide a service naming. And there is a logic on how these are named together, which means we should be able to, using basically machines, we should be able to understand by looking at these namings that we can get from the service registry, which we can then, from the service, the system, and device registry, we should be able to restructure how is this put together and working right now, which means that we can have an instant picture of what is connected and which data streams, which service exchanges is actually in operation and orchestrated right now. So what do we have in technology? What's there? This is the big picture on what people are working on for various reasons today. From lower level, the local cloud basic stuff, security, service exchange support, inter-cloud service exchanges, system of systems support, execution support for productions, for example, supply chain product lifecycle support, test and management support. And those with, I would say, solid currency, those are released, and the others are more experimental, but there are people working on all of these yellow boxes, and there might be boxes which I haven't captured yet, but this is what's going on. And if we look at this picture, this is what currently is released as version 4.1.2. There are to be honest, the translation system, the data manager, is not released yet, but they will be released in the coming few weeks. Most likely during a meeting in Gothenburg in 2.5 weeks' time. And just to briefly walk through some of these core systems, I will be pretty quick on this. So the objective of the service register is to be able to record all the services available and to be able to find them. And there are some details on that. The authorization system is to be able to do this authentication of the consuming system and to authorize the service consumption. And we also have now the capability of doing accounting, so we can see how many times or telling that an authorization is valid for a certain time or for a number of consumptions and so on. The orchestration system is, we had an explanation of that a few minutes ago. And these three systems are always drawn in blue, red, and green color. Just to know that this is a color coding that we use for helping us in the engineering of this. We can skip this. But it's support core system, the plant description. Back to how do we describe this in at least 3 dimensions. There will be extensions to more dimensions. And how can we help ourselves in creating the orchestration rules? And this is part of what we certainly will work with more in the Arrowhead Tools project, how we can really improve these and how we can connect this to existing engineering tools that's out there. So this is the prototype that has been created so far. The configuration is how do we configure individual software systems or devices and do updates of parameter settings, etc. Can even include updating code on updating the software, the code on a software system. System registry is to keep track of which are these software systems that are actually onboarded in the local cloud, and device registry is the same, but for the individual hardware that's included in the local cloud. The event handler, I spoke briefly about that previously, and the quality of service is to basically monitor latency to start with, and then be able to help you in tuning this, how the network will work within a local cloud. There's a data manager, which is there for keeping track of things, so audits. I see I have an old name, it was called Historian previously. Sorry for that. But it's kind of an interesting experiment coming up. Intel has become quite interested in this together with a company, small kind of spin-off company here from our university, and they are now targeting to have data manager capacities of storing 250,000 to 1 million data points per second in an Arrowhead local cloud. We hopefully will get that clear and release data on this, I would guess after summer sometime. So it means that performance-wise, we can probably do as good as anything else that's right. The important gatekeeper and gateway, so being able to talk in between various local clouds. And this picture is just to illustrate that the gatekeeper is doing the administrative part, meaning and talking to the blue, red, and the green system within this local cloud and doing this and checking that we can do the lookup between various clouds, we can do the orchestration between various clouds, and that we can authorize consumption of data between various clouds. Once that's done, the gateways will actually then have where is the other local cloud located, and these gateways will have the information which is the service to be consumed from this local cloud and how that can be transferred to, for example, an HMI in the lower local cloud. And this exchange, the green lines here, is always using MQTT as the protocol, which is mandated for this intercloud communication in the current implementation, and has been proven as a very high security way of transferring data over open internet. Yeah, so this is some more on the local cloud and the gatekeeper gateway. We also have this protocol translation, where a consumer understands protocol A and the producer understands a protocol B. They have different encoding and different semantics, where we would like to translate between these. To translate the protocol and the encoding can readily be done, but semantics is a problematic part still. And there is a working translation system, and there are currently available translations between REST, co-op, MQTT, and to FiWare. There is partly solutions for OPU, OpenCUA, for IDS. We have Polish partner DAC who is working on the integration with IDS, and also Fraunhofer has provided translation between Arrowhead and DASys, a German project. And in the end, we need to build application systems, and this is normally where most people will end up, and only using the existing Arrowhead Framework core systems. And then let me move on to the final little presentation. There's just a few minutes left till 12 o'clock, and I will end on time. So my last set of slides are very few. So where do we find code, installation and application examples, and so on, and what is documentation available? This is the last part here. So Arrowhead Framework went open source in spring of 2016. The current release is version 4.1.2. There is a project homepage. Let's see whether we can show this to you.
You muted yourself by accident.
Oh, sorry. Sorry, I'm speaking too fast. So I'm just backing off. So where that link took me to is the Arrowhead Framework, which is in parallel to the Arrowhead Tools homepage. And we can get some more information on this, the architecture and the descriptions and how to implement so on. And this was just provided a few weeks ago, so it's not complete. And some of these links you're going to end up in the old homepage of the Arrowhead Framework, and the old one will look something like this. So this is the old homepage of that. There is a book that was written a few years ago. Quite valuable, a lot of these definitions that I've been speaking about, and a lot of details on that. But there is also a number of description of use cases that was tested during the Arrowhead project, where people actually value the potential usage of the Arrowhead framework as a way of implementing their automation digitization solutions. Let's just get back to the slides. So the book is from CRC Press, and it's basically me as an editor, but there are, I don't know how many authors of the various chapters there. So it's still available from CRC Press. If we move on, there is code to be found at GitHub, and the place is github.com/arrowhead-f. And let me move again to the browser. And this is where you end up, and where you will find a number of the released tools and examples and so on. And if you want to go and install this is the core Java directory, and this is where you will find all the necessary code that's there and the instructions on how to install this. Of course, there is the bare metal way of doing it. There is also a very nice way of installing this on Debian-based Linux machines that is very automated, and you just go through a guided set of questions, and will basically compile for you. Of course, there will still be some hands-on at certain places, but this is also will be extended a lot more in a very short time frame. How to support this? There is not a release yet, but there is a Docker installation mechanism as well, and you can basically find that if you go to development project here, so you can find these kind of things as well. Just to show that this is really no magic, I can turn to my own little I have a virtual machine with Linux, Ubuntu Linux working. So let me just share that one and just show that we have. Where is that one? There we have it. So now you should see my Ubuntu screen, and I'm basically now you see I've installed the Arrowhead. I have the core Java systems there, and just to see what's there, we have authorization, gatekeeper, QS, certificates, gateway, documentation, orchestrator, service registry, and event handler is everything installed there. And I can simply start this by going to the scripts and just running loops. Where is it? This one, and we can get this start the various systems, and this is right now done in what's called the insecure mode. And there we are, and we can right now see that I have 5 Java systems actually running. Doesn't tell us more than that, but this is what's up and running. Let me move back to my presentation. So This is where you will find code. There is a number of tools. There is a management tool and those kind of things where you can get things up and running. And I'm very glad to hear that there is people that's already experimenting with this. So this was hands-on in brief. We will provide hands-on in detail. There is a workshop June 11, 12, 13, basically by the Productive project, but day 2, June 12, Wednesday, June 12, there is a meeting in Gothenburg to which we can invite you. Those that want to come there will be a small participation fee. But if someone interested, please put me an email. I will try to get you in. There will be sessions on hands-on sessions, installation, how to use existing client libraries, how to create a service producer system, how to create a service consumer system, look into Arduino skeletons, management tools, test tools, workflow manager, data manager, and Serviceoriented cloud service exchanges. All this will be prepared, and people will be ready for supporting you guys in trying to use this. Each of these sessions will be a 5 to 15-minute kind of introduction that we will record and transfer over Webex. So it would be possible to attend these sessions online. But of course, being on-site will be, I guess, much more productive. So this is the next step in what we can provide as introductions of using the existing Arrowhead framework to the Arrowhead Tools project. So sorry for being a few minutes over time, but compared to when we start, I think I used the 2 hours. Anyone having a comment or a question to what has been discussed today?
Yes, Jerker, I have a question. How to get feedback for the framework for the software? Shall we use GitHub issues or mailing list, or how to get into contact with developers?
GitHub issues and the tracker system there, and there is also what's it called? There's a Slack. Track for Arrowhead framework as well.
Okay, and where is the address of the Slack? I am not aware of that.
Should be somewhere on the GitHub. Honestly, I don't remember right now.
I will try to find. Thank.
Yeah. So, and the primary guys that probably will respond to you is Svetlin and some of his colleagues at the ICEA company in Budapest. These are in charge of handling the GitHub repositories and the tracker and the Slack. Yeah. Anyone else that has a comment or question? No? Then I would like to close this and say thank you very much. I'm very grateful for having this huge audience today. I haven't counted, but it looks like at least 50 plus people. So I hope this has been valuable. If anyone has comments, please put me an email on that. Otherwise, I would say thanks for today, and hope to see some of you in Gothenburg, and also some of you online for the Gothenburg session. Thanks for today.
Thanks a lot, Jerker.
Bye. Thank you. Thanks. Have a good day. Bye.
Thank you. Goodbye.
Hi. Have a nice day.
Hi. Have a nice day.